When a river or lake runs blood red, our instincts sound an immediate alarm. Humans are hardwired to associate this color with decay or ancient plagues. Yet scientists often treat these unsettling environments as high-priority research targets rather than disaster zones. While the water looks like a crime scene, the harsh chemistry required to create this pigment often supports some of the most resilient and specialized life forms on the planet. In the McMurdo dry valleys of Antarctica, a 5-story high crimson flow leaks directly out of the Taylor Glacier. Researchers call the site Blood Falls. Underneath millions of tons of ice sits a pressurized subterranean lake that has remained sealed off from the outside world for 2 million years. The water in this subglacial reservoir is saturated with dissolved iron. When it escapes the ice and contacts the atmosphere, the iron oxidizes. It reacts exactly like this rusted metal, turning the outward flow deep red the moment it hits the air. Living within this rusted brine is a microbial time capsule. Bacteria have survived here for millennia in total darkness, isolated from the energy of the sun. These organisms persist by extracting energy from the surrounding minerals, proving that biology can thrive without the standard requirements of oxygen or sunlight. In southwestern Spain, the Rio Tinto flows in a thick crimson ribbon for miles. The water is defined by heavy metal saturation and a level of acidity high enough to dissolve iron. Despite these conditions, the river is teeming with specialized bacteria. These organisms sustain themselves by feeding directly on the dissolved iron and sulfur found in the riverbed. NASA astrobiologists use the Rio Tinto as a primary analog for the surface of Mars. The iron-rich, barren landscape of the red planet shares a nearly identical chemical profile with this river. The Rio Tinto shows that life can utilize harsh chemistry to survive on worlds we once considered completely sterile. Tanzania's Lake Natron is saturated with volcanic salts and extreme alkalinity. These conditions allow salt-loving bacteria to bloom in massive numbers, painting the water a fractured red. This high concentration of sodium carbonate is lethal to most complex biology. Animals that die in the water are gradually calcified, their remains mummified into stone-like shells on the shore. However, this caustic chemistry also prevents land-based predators from entering the water, turning the interior of the lake into a protected zone. Millions of lesser flamingos rely on this toxic barrier for survival. They build their nests on mineral islands in the center of the lake, safely isolated from jackals and hyenas. At Lake Natron, the same minerals that calcify one creature provide the essential security another needs to raise its young. While some red waters are permanent features of the landscape, others appear almost instantly. Historically, these sudden shifts were often interpreted as supernatural warnings. This phenomenon is an algal bloom. When temperatures rise or nutrients spike, specific red microalgae divide exponentially, saturating the water column with their pigment in a matter of hours. These blooms can cover miles of coastline. As seen from above, the algae aggressively claim massive sections of the ocean, moving with the currents. This color change represents a sudden burst of biological activity, as microscopic organisms capitalize on a brief shift in local conditions. From the ice of Antarctica to the shores of Tanzania, these waters function as specialized ecosystems for life forms that thrive on the edge of what's possible. We often mistake extreme survival for environmental failure because these habitats don't fit our standard definition of habitable. Nature demonstrates that even in freezing ice or caustic acid, life finds a way to turn the most hostile chemistry into a home.